Hello class, welcome to the next segment in lecture 23, and in this segment we're going to take a look at some of the features that we look for in the atmosphere when diagnosing the potential for flash flooding. So let's go ahead and dive right into it. So just like with the damaging wind segment, there are actually multiple different mechanisms that can come into play when to produce flash flooding in the atmosphere. So we're primarily going to highlight the different combinations of characteristics that can favor flooding and talk about characteristics that are universally detrimental to a flooding threat. So one such characteristic is actually the amount of moisture that's present in the atmosphere. Ideally, you want very rich tropospheric moisture levels. If you've got deficient levels of tropospheric moisture, then you're not going to have as intensive rainfall rates, so that means that your potential for flooding is going to be significantly lessened. And there are a few parameters that you can look at to diagnose the potential for flooding. One is referred to as precipitable water, which is often abbreviated as PWatt or PW. And in, say, something like the plains, you ideally would want to see a value over 1.5 inches. The way that this parameter actually works is you take all of the water that's present in the atmosphere that's been sampled. So if you take a look at the sounding, you take a look at all of the moisture in that sounding, you pull all that moisture out, and then convert it all into liquid, and then see what the height of that liquid is. So if you've got precipitable water of 1.5 inches, that means if you take all the moisture out of the column of the atmosphere that you just sampled, convert it all to liquid, and then measure the height of that liquid, then you would get a height of about 1.5 inches. So high values of precipitable water typically mean you've got a very rich moisture levels throughout the entire troposphere, which can indicate that you're going to have very efficient rain production. Now, something that's very important to keep in mind about this parameter is it is also heavily dependent on the depth of the atmosphere that you're sampling. So in the case of the plains, where you're sampling from about 1,000 millibars to the height of the tropopause, which might be around 200 or 300 millibars, you're going to get a much higher precipitable water value than you might get, say, over the Rockies, where you're sampling from 850 millibars to the same height. So your precipitable water values over higher elevations are going to be underreported. They're not going to be as high as a region where you're sampling a much bigger chunk of the troposphere, again, from, say, 1,000 millibars to 200 or 300 millibars. So that's just something to keep in mind when you're using this parameter. Keep in mind that you also have to look at the depth of the atmosphere. If you get a small value of precipitable water, but you've got a smaller depth, then of course that value of precipitable water is going to be smaller, but there might still be enough moisture to produce flooding. And one case of this was the flooding that hit Denver a few years ago, where the precipitable water values were at best an inch, but for that region of the country, an inch of precipitable water is a ton of water in the troposphere. So just something to keep in mind that this parameter, favorable values of this parameter can vary widely depending on where you are at certain geographic regions. Another thing that you ideally look for is high values of dew point, usually over 65 degrees Fahrenheit. But again, this can also vary depending where favorable value of dew point can also vary depending on where you're at a specific geographic region. So again, if you're up in the Rockies, your dew point near surface, which is going to be around 850 millibars, might be relatively dry compared to a dew point that you might get over the plains. So just something to keep in mind. There's a significant amount of geographic dependency. It depends on where you are geographically. That's something you want to keep in mind when you're going to diagnose these parameters that we're showing on the screen here. And the same thing for this parameter. K-index, which is sort of a empirical thermodynamic calculation, which is used to assess the potential thunderstorm coverage that can be expected in the atmosphere. There are also things that can skew this value, but ideally what you want to see is a very deep and moist layer extending up to about 850 millibars, and then shallow lapse rates extending to about 500 millibars, and ideally above that if you want a higher end flooding event. And also, just like with tornadoes, if you want a high end flooding event, you want low LCLs. Because if you have low LCLs, again, you have less evaporative cooling. If you've got not as much water evaporating, that means you're going to have more liquid water able to reach the ground. More liquid water reaching the ground means the greater potential for flooding to occur. And something else that you want to see is you want to see shallow lapse rates of the entire troposphere. And the reason why you want to see that is because you don't want a lot of cold air coming down to the ground level which would tend to disrupt the thunderstorms that are in progress. If you have really shallow lapse rates, you're going to have less in the way of cold downdrafts, which means your thunderstorms have a chance to remain over the same area for longer, but they also have a better chance of not having their updrafts undercut by downward descending cold air. And you don't necessarily need strong vertical wind shear for flooding. You can get away with, say, moderate vertical wind shear, maybe surface 6 kilometer shear of 15 to 30 knots. Ideally, you want more shear for flooding to increase the longevity of thunderstorms. But just like we mentioned in the previous lecture, you can get a significant flooding event from a single cell thunderstorm, which exists in an environment of weak vertical wind shear. The reason why that can give you significant flooding is because the single cell thunderstorm doesn't move much, and it also doesn't. It also just it just doesn't move much, and it's just dumping rain endlessly on the same location. But usually, a single cell thunderstorm just doesn't last very long. Usually, doesn't last long enough to produce flooding. But if you happen to get a single cell thunderstorm that is sufficiently long-lived, then you can get locally significant flooding to occur. But ideally, for a nice widespread flooding event, you want some degree of vertical wind shear, which will help maintain more long-lived updrafts. And this is where the mechanisms start diverging. So one of the mechanisms that we just talked about is just a thunderstorm that just sits over the same area for a really long time. That's one way to get flooding. Another way to get flooding is to have lots of thunderstorms all tracking over the same area. So the individual storms might be moving very fast. They might be moving 30, 40, 50, 60 miles per hour. But if all the thunderstorms are tracking over the same area, then they're just dumping large amounts of rain over the same areas, which is going to result in flooding. So you can have flooding events from fast-moving thunderstorms, but slow-moving thunderstorms that don't move much or just sit in the same area for a really long period of time, that can also result in flooding. And finally, the last characteristic, which is not really atmospheric, but is something that can make forecasting flooding particularly complicated, is you have to know something about the landscape itself. You have to know something about how the soils, some properties about the soils, and also whether you've got rough terrain or relatively smooth terrain. Because if you've got saturated soils, that means you're going to have soils that are not going to be absorbing water as readily, which means you have a better chance of having liquid water accumulating on the ground, which is going to increase your risk for flooding. And similar for impermeable surfaces. So something like red clay, which is something that we see a lot of in Oklahoma, that is very much an impermeable soil. It's very hard to get water penetrating through something like red clay. And another thing that's hard to get, another thing that's really hard to absorb water is a very urbanized landscape. So if you're in a region where there's a big city and you've got lots of concrete and other artificial surfaces, those surfaces really don't absorb water very well. So those will accumulate water much more rapidly than, say, an open landscape that has pretty much all just grass and dry soil on it. And then hilly terrain can help funnel all the water into a common area. So if you're in a valley and it's raining very hard, then all that water is going to be coming down the slopes and focusing itself in the base of the valley, which can result in significant flooding. But also in rough terrain, you're also much more likely to get landslides and rock slides if you've got sufficiently intense rainfall rates, or if the soils on the sides of the hills are sufficiently saturated. So here's a look at a sounding that actually featured a fairly high-end flooding event. I wouldn't call it a particularly high-end flooding event, but it was definitely higher end. And this was actually driven by supercells all tracking over the same area. So if you take a look at the wind profile here, you can see that the storm motions, they want to move quite fast. But in this case, there were actually multiple supercells that were tracking over the same area. And if you take a look at this environment, you can see some of the stuff that we talked about. So the dew point's really high. It's 69 degrees Fahrenheit. That's definitely above 65. K-index is around 36, so right about the same threshold that we outlined earlier. The lapse rate's pretty shallow, so those thunderstorms aren't going to be producing a whole lot in the way of downdrafts. And you can also see that in the decape. It's only 240 joules per kilogram. And the precipitable water value here, if you can read that, that's 1.83 inches. So there's a fairly significant amount of moisture present in this atmosphere here. Most of it appears to be concentrated below 500 millibars. Above that, it's pretty dry, but there was enough moisture here to result in some flooding from multiple high precipitation supercells that were tracking over the same area. But that's going to do it for this segment on flooding. And in the next couple segments, we'll take a look at some of the some of the textbook synoptic scale setups that you would look for, or synoptic scale features that you look for to diagnose both tornado outbreaks and straight line wind events, derechos. So with that, I will see you all in the next couple of segments.